An example of an ionic compound is lithium fluoride. An example of a molecular compound is H2O. Now, molecular compounds are also called molecules. Here's just a quick reminder. Ionic compounds are composed of metals plus nonmetals. On the other hand, molecular compounds are composed of nonmetals interacting with other nonmetals. These two types of compounds are very different. Their differences can be attributed to the type of bonds in each. An ionic compound has ionic bonds. In a molecular compound, the atoms are held together in a molecule by covalent bonds. Now, electron configurations show how and why atoms form different types of bonds. So when you think electron configuration, what should you be thinking? When bonding happens, atoms share, gain, or lose electrons in order to achieve a more stable electron configuration. The most stable electron configuration is that of a noble gas. So atoms will share, gain, or lose electrons to try to achieve a more stable configuration. Let's take a look at this electron configuration one more time. So what element is represented by this electron configuration? Look at your periodic table and you should come up with the element of sodium. Sodium is represented by Na. So my question to you is, would sodium be more likely to share, gain, or lose an electron? What I need to do is I need to look at my valence electrons. My valence electrons are the outermost electrons in an atom. So I look for my largest number, which is 3. That is my outermost energy level. In my outermost energy level, I have an s orbital that has 1 electron in it. So I have 1 electron in my outermost energy level. I have 1 valence electron. So, is it more likely for that 1 valence electron to leave the element, or is it more likely for sodium to gain 7 other electrons so it can obtain a noble gas configuration? It's much more likely for sodium to lose that 1 electron, and that's exactly what happens. Sodium forms a cation because it will lose that electron. If it loses that electron, the new electron configuration of a sodium cation is 1s2, 2s2, 2p6. That's the same electron configuration as a noble gas. Here's another electron configuration. This is the electron configuration of chlorine, represented by Cl. Is chlorine likely to lose, gain, or share electrons? In this case, we're going to be specifically speaking of ionic bonding. I'm going to bond chlorine and sodium. So we're speaking of an ionic bond. I first need to look at my valence electrons. I look here and I see a 3 and a 3. Those are my largest numbers. Those represent the outermost energy level. So my valence electrons should be 2 plus 5. That's 7 valence electrons. Well, 8 valence electrons represents a noble gas. So is it more likely for chlorine to gain 1 electron, or is it more likely for chlorine to lose all 7 of those so that the outermost valence, meaning that would be gone, the outermost valence would have a total of 8 electrons. It would have the electron configuration of a noble gas. It's much more likely for chlorine to just simply gain 1 more electron. If that happens, it will form an anion. Let's write that out. It will be Cl minus. Okay, so now let's look here. We have Cl minus and Na plus. We have a cat ion and an anion. Let me write those words for us. Cat ion and an anion. The way I remember that, I think cation, there's a T that looks like a plus sign. so I always know it's the positive one. They will combine to form an ionic bond. NaCl should look familiar. In past chapters, we have dealt with that ionic compound. Sodium loses an electron. Chlorine gains an electron. Well, where does that electron come from that chlorine gets? Well, it gets it from the sodium. Both of them are happy or complete. They are more stable because they both now have the electron configuration of a noble gas. Again, here's chlorine. If there's just one more electron here, that would make that a 6. That would make that a complete octet. Up here, it would lose that one electron, it would give it to chlorine, and then it would have its complete octet. Both of them would have the electron configuration of a noble gas. In the simplest form of ionic bonding, there is a transfer of 1 or 2 electrons from a metal to a nonmetal. In our example, we used sodium and chlorine. So sodium would be losing 1 electron, chlorine would gain 1 electron. Now, in an ionic bond, what holds those together? Electrostatic forces hold the two oppositely charged particles together. So it's the electrostatic forces that hold ionic bonds together. We've talked plenty about ionic compounds. In ionic compounds, there are ionic bonds. There's a transfer of electrons in ionic compounds. What about molecular compounds? We know molecular compounds are held together by covalent bonds. Now, is there a transfer of electrons? No. In molecular compounds, which are held together by covalent bonds, they don't gain, they don't lose, they actually share electrons so that each of them is stable because they have that noble gas configuration. So we actually share electrons. We've briefly talked about the two extremes in bonding, ionic bonding and covalent bonding. Now don't get confused. I know I told you that those were the two main types of bonding. Well, it actually happens on a spectrum. So something that is purely ionic is a complete transfer of electrons. The example we used is pretty ionic, NaCl. Compared to a covalent bond happens between a nonmetal and a nonmetal. So let's go ahead and give ourselves an example, the chlorine diatomic. Now, this diatomic, there's actually an equal sharing of electrons between the chlorine and the second chlorine. So between those two, there's an equal sharing of electrons. One chlorine's not stronger than the other, pulling the electrons towards it. The electron pair sits pretty much in the middle. So that is purely covalent, meaning that it's equally sharing. What about something like hydrogen and fluorine? This is an example of a covalent bond, right? The covalent bond would be between the hydrogen and the fluorine, but would it be equal sharing? There's a new word for us to know, electronegativity. Let me write that. Electronegativity is the ability of an atom to attract electrons towards itself in a bond. So for example, HF, that's in a bond, so fluorine has a higher electronegativity than hydrogen. The electron pair that's sitting between the fluorine and the hydrogen will be pulled towards the fluorine because it is more electronegative. We have two more vocabulary words that we need to add to this. We have polar and nonpolar. Polar and nonpolar are two important vocabulary words. A polar molecule is a molecule that has unequal sharing of electrons. So it's not purely covalent. It's probably found somewhere right here on the spectrum. It's definitely not a transfer of electrons, but there is unequal sharing. A good way I like to remember this is polar. So for example, if you have fluorine and hydrogen, the fluorine will pull the electrons towards it. Polar. it'll pull them towards her. That's a funny way to remember it. It helps me. Now, nonpolar is an equal sharing of electron pair. So the chlorine diatomic, the two chlorines are sitting there. Well, they're both the same element. So they're going to be pulling at that electron pair that sits between them equally. So it is a nonpolar molecule. So let's just recap real fast. So there are ionic compounds and there are molecular compounds. Ionic compounds have ionic bonding holding them together. Molecular compounds have covalent bonding happening or holding the atoms together. It is on a spectrum. So on one extreme, it's ionic bonding, and that is the complete transfer of electrons. On the other extreme, there's covalent bonding, which is the equal sharing of electrons. But covalent bonding can be divided into two types of covalent bonding. We have nonpolar, which is the equal sharing, and we have polar, which is the unequal sharing of electrons. Now, in section 8.2, you'll learn more about ionic bonding. In section 8.3, you'll learn more about covalent bonding.